Hi everybody, welcome to our first video on improper integrals. In this video we're going to find out how we can compute an area where the limits of integration aren't just finite, a to b, but something more like a to infinity. No and beyond. Sorry, stop at infinity. So let's do an example here. Say I wanted to know the area under 1 over x squared from 1 all the way forever and ever and ever. Now, a reasonable expectation is that it just doesn't make sense. You keep on adding more and more area to this thing, and eventually that should just blow up to infinity. On the other hand, you might reasonably think that, well, this is getting smaller and smaller and smaller, and so you're adding less and less area. Maybe somehow it's bounded by something, right? It just never gets to some higher number. So the way we're going to handle this is by saying, well, okay, what if we cut it off somewhere? Cut off right there at some b. Yeah, I could definitely compute that area. How would I do it? Well, I just compute from here the integral from 1 to b, 1 over x squared dx. And that will give me some value. What if I start pushing b out further and further and further? But I always stop it somewhere. If I stop it somewhere, again, I can compute that value. And so I'm going to get a different amount of area. It should be getting bigger, right? We can see from the picture. Question is, as b goes out to infinity, does that area that I get by moving b out further and further converge to anything? Does it get closer and closer and stay close to some specific value? We need a limit. That's what we're getting at here. So the way we're going to define an integral of this form, integral from, say, 1 to infinity, is we're going to define it as the limit of the process where we let b go out to infinity. So in symbols, we would say that this integral is defined as the limit, as what? Well, we'll say that in a second. We're going to integrate from 1 to b, 1 over x squared dx. And what do I want to do? I want to let b go to infinity. All right. So instead of defining this directly as just saying, well, it's the area under the curve, which may not exist in the first place, we don't know what that means, we're really going to define it using a well-defined mathematical operation, namely taking the limit as b goes to infinity here. Now, the nice thing about doing this is it means I don't have to worry about this until the very end. I'm going to keep writing it, okay? And in fact, you should always write your limits. If you don't, you annoy your instructor. But I'm going to just copy it until I'm actually going to do it, okay? Until I actually take the limit. Until then, I just compute this like normal. So let's see. Limit as b goes to infinity. And now, what's an antiderivative for 1 over x squared? Well, let's see. 1 over x squared is x to the negative 2. Add 1 to negative 2, you get negative 1. Okay, so it's negative 1 over x, and I integrate from 1 to b. Okay, I can now use my fundamental theorem here, just write the net difference. So the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. And now at this point I stop and I ask, okay, what's happening as b goes to infinity? As b goes to infinity, this guy, what happens? 1 over b. As b gets really, really big, 1 over b gets really, really small. Forgetting about the negative, I don't care about that. 1 over b is going to 0. It's getting smaller and smaller, right? 1 over a billion, 1 over a trillion, 1 over a gazillion. Is that a number? Well, at least 1 over a Google. Brought to you by Google. It's getting really, really tiny, okay? Getting closer to 0. So the limit of this guy is 0. And then, well, this guy doesn't depend on b at all. This is just minus 1. And so the limit is actually 1. The area underneath this curve, as you go out starting at 1, all the way out to infinity, is amazingly just 1. Okay, that's wild. Okay, now once you do this one example, you might start thinking it's always going to work. And it might, but let's see another example. We'll be back in a moment. All right, welcome back. So I've changed up our function a little bit. Instead of 1 over x squared, we now just have 1 over x. But I want to integrate the same region, 1 to infinity. So that's what I'm interested in. The integral from 1 to infinity, 1 over x dx. And last example, we saw that you actually could get this to be a finite number, and this looks pretty similar. So our expectation should be that it will also converge. Of course, if it did, then there would be no point in doing this example. So our expectation should really be that it won't converge. Of course, why then am I even doing this in the first place? Once you know that it's not going to converge, there's no sense in doing it. So you might as well assume that it does converge. Ooh, this could go on a while. Inconceivable. Okay, let's just do the problem. So first, how do we actually compute an integral where the limits are infinite? Remember, I don't want to compute it when it has an infinite limit. I want to compute it when it has a finite limit. So I cut it off somewhere. Again, we'll call it something like b. So I'll take an integral as x goes from 1 to b, 1 over x dx. But I don't want it to stop at b. I want it to go to infinity. So I take the limit as b goes to infinity. Okay, fine. I just need to compute this integral. I don't need to worry about the limit until the very end. So I'll just leave the limit lying around. What is an antiderivative for 1 over x? Okay, that was natural log of x. Good. So I get the natural log, and normally we would put absolute value of x, but since all my x's are positive, I don't have to worry. So I have ln of x between 1 and b. Okay, I copy my limit again. And now, by the fundamental theorem, I take ln of b minus ln of 1. Now, normally, it's at this point I'd like you to kind of recall what is ln of 1, since people tend to forget that quite easily. But we're not even going to need it, because look at this first bit. We have the limit as b goes to infinity of the natural log of b minus, well, just some constant, whatever it is. It's 0. What's happening as b goes to infinity to ln of b? Well, this would be a good time for you to write down a graph of the natural log function. You can't do it? Okay. It's something you should know. Okay, if you can't do it, learn to do it. This is very important. Okay, I'm going to sketch it up here for you, but next time I won't do it. Natural log function is going to look something like that. Now, as b goes to infinity, this just blows up. So this guy is not going to become some finite number like 1. It's going to infinity. So in this case, we're going to say that this integral diverges. And I would usually add to infinity. There are other ways of diverging where it doesn't seem to go to any number. Maybe it's just alternating, going up to 1, back to -1, and so forth. But this is a specific type of behavior. The area just keeps on getting bigger and bigger and bigger, and it blows up to infinity. Now, logarithms don't grow very quickly. So it means it goes to infinity pretty slowly, but nonetheless, it goes to infinity. Okay. Now, in the next video, we're going to see a different way of testing whether or not an integral converges or diverges. It's not exactly going to be computing antiderivatives. In fact, all we're going to do is try to compare an integral we don't know to one we do know. And once you know it, it's going to be called the comparison test. Okay, we'll see you next time.